Hello, welcome to a new lecture of Math-S401, Dynamic Optimization. In this lecture, we're going to continue where we left off on the previous lecture, namely on the implementation of the Bellman equation on a computer. So, if you remember, our problem was the following Bellman operator, that TV of a state x equal to the maximum of A in G of x of our instantaneously payoff function xa plus beta v a. And here I take the case where the law of motion is simply the identity. Okay. So as we see it, if you want to implement this, then basically we have to solve this maximization problem over and over and over again. Each time we get a new iteration of the function, and then we substitute it back into our objective function. So we get a sequence of functions, and this sequence of functions approaches our desirable fixed point, right? This is where we want to go to. So we generate a v0, a v1, and so on, and this converges in the limit to our v star. So we have seen that the speed of this algorithm depends greatly on the maximization thing, right? So maximizing a function takes quite some time on a computer, and this is probably the most expensive part of this whole procedure, except for the fact that, well, it depends on how many times you have to compute this new function. Okay, but every time you compute this function, you have to make this maximization problem once more. And how many times per iteration do you have to do this maximization? Well, if our state space is given by the grid x1 until xn, then basically for every value of x, we have to run this maximization problem. Okay, so at each iteration, run n maximization problems. Okay, so you can probably get some efficiency gains by decreasing the number n. Okay, so if you would want to compute the fixed point function v, then here we have our state space x. So we have our grid, right, which is a set of points, and basically for every point here we get an estimate of our value function, right? And what we normally do is then we somehow say, okay, we probably will interpolate. So in between the values, the function v will look like this. So in many cases, it's not really necessary to compute this function on a very fine grid, right? So for example, if I would say, okay, I don't want to run this maximization problem n times, but I want to run it in a few number of times. So basically what I'm doing is I'm restricting my grid to a smaller grid, right? So a grid with fewer items. So maybe I will only compute it here, 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 and here. Then maybe I have a value here, 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 and then probably I'm happy enough by interpolating between these between all these points, right? So in other words, a good idea could be to decrease n, right? So if we decrease the grid, then we only have to maximize this function a fewer number of times. Okay, so this is a sensible thing to do. However, there are two things that you have to take into account. First of all, you're going to compute the function on a fewer number of grid points, which might seem a reasonable thing to do. But then we also want to make sure that these points that we're going to compute are actually quite good, right? And this will depend on how good this thing, the maximum, is actually going to approximate this function. Okay, so let me try to explain the problem here, right? So you want to maximize with respect to a and gx of f xa plus beta va, right? So this is our maximization problem. So now, first of all, we can compute this for fewer number of points x. But normally, if you decrease x, right, if you decrease the size of x, normally our a is going to be an element of x, right? So if you decrease the size of x, then you're only going to optimize on take the maximum over a fewer number of points, right? By decreasing x, you're also going to decrease the number of potential a values. So in this sense, this might be a very bad approximation, okay? Because here you're going to evaluate v and f at only a fewer number of points, right? So the idea here of interpolation is indeed we're going to compute tv, all right, or the functions v on a fewer number of grid points, but we would like to keep the dense grid on the decision variable a. Okay, so the maximization is going to be over a dense grid, but we're only going to evaluate it at a fewer number of points. Okay, so the idea is to keep a, or the decision variable, on the dense grid. Okay, so the value of a that's going to maximize it is going to be a very good approximation to the continuous one, right? Because we're looking at a very dense grid for a. But change x, right? So the values of x on a small grid. So we're going to compute the function v only on a few number of points, but we're going to let a vary over a dense grid, right? So the optimal value of a that we're going to get is going to be a good one, and as a consequence, the value of tv is going to be a very good approximation to the true value. Okay, so that's basically the idea. Now there's a problem, of course. If x, for example, x1, x2, x3, and so on, xn, if this is the grid for the x, and then you say, okay, for a we want to have a denser grid, right? So for example, you want to have here, but then between x1 and x2 you also want to have a couple of points, and between x2 and x3 you want to have a couple of points, and so on, right? So this is a denser grid for the a. Well, we need to evaluate v here at this particular choice of a, which might lay between two other points. Okay, and if we encode v as we did previously, well then v was a vector v1 until vn, right? So this was an n-dimensional vector because basically in the previous round we computed it on this grid here, but now we also want to sometimes evaluate it at points between other values of x. Okay, so v is computed at a small grid, but we want to evaluate it at the dense grid. Okay, so how do you evaluate a function on points where it's not defined? Well, for this you can use what we call interpolation. Okay, so the idea is very simple. So here you have your state space, this is your grid. Okay, so for example you have this point, this point, this point, this point, this point, and this point, right? These are the v values that you compute for every x. You have one, and now maybe you want to evaluate it at this point, so you have no idea what it is. So you think, so what do you do normally? Well, you draw somehow a function through all these points, right? And then you say, okay, at this value probably my v value will be at this point a here, my v of a will probably be between this point that I know and this point that I know, right? Some interpolation between these 2 points. Okay, so that's what basically we're going to do. Here we're going to take the maximum over a dense grid, but this value here that we're going to compute, this is going to be an interpolation, right? So we can write it as v star or v bar or something, right? So this is now going to be an interpolation. Okay. So in most software packages, you can find various kinds of interpolation functions. So probably the most well-known is what's called the linear interpolation. Okay. Then, for example, if you have a couple of points like this, This is my v function. Okay, so let's say that you want to evaluate this point here. How do you do this? Well, you look at the value below, just below a, that's on the grid. You look at the value just above a, that's on the grid. So these are the function values, and then you just draw a linear line, right? So this is linear interpolation. You draw a line between these two, and you just take this value here. Okay, that's linear interpolation. Okay, and linear interpolation is easy enough such that actually we can write a program to do this. Okay, so that's the goal of this lecture. Basically, we're going to modify our program that we have seen previously, and we're going to modify it to take into account linear interpolation. So let's think a bit how we can do this. Right, so we have values of x. Right, so this is my x1, this is the first value of x. At some point we have xn. Then we have the value at a at which we want to evaluate this function v. We will have an xn plus 1 until x begin. Okay, so first thing, in order to compute this value, right, so this is now my v1, right? So remember, big V was this vector v1 until vn, computing the values of at x1 until xn, right? So this is vn, this is vn plus 1, this is vn. Okay, in order to compute this value, first we need to find the index here, n, and we need to find xn plus 1. So we need to know the values of x for which a lies between xn and xn plus 1. So first case that may happen is that a is below x1. Okay, so if a is below x1, well, there's nothing to interpolate here anymore. So what we can do is we can say, okay, maybe we can take the constant functions outside the domain here, right? So if a is below x1, then we just going to return the value of v1. Okay, and maybe I should here put x1, so the first element at the vector x, using the notation of the previous video. So here, in defining a function, let's call it interpolate. Okay, so the interpolation is going to take a value a at which we want to evaluate the function. It's going to take our vector x, and it's going to take our vector v of values. Okay, so if the point at which we want to evaluate is before the first value of x, we're going to just put v1. Else if a, you can make this less or equal or greater or equal. If it's further beyond xn, right, it's greater or equal to xn, then we're going to return vn. Okay, so we make it constant here, and then else. Okay, so what do we do now? Once we have an a, we need to compute this here, and we need to compute this here. So how do we obtain this value? Well, first of all, we can measure the distance between a and x1. Okay, a minus x1. And then we can divide it by the size of every interval. Okay, this is going to be, for example, x2 minus x1. This is like the step size of the grid, right? Here we assume that all x1, all distances are equally spaced. Okay, so what's going to give me? This is going to give me a number. Basically, it's going to count the number of steps 1, 2, 3, 4, 5, and so on. Okay, but this is not going to be an integer, so I'm going to convert this. I take the floor of this one. This is going to tell me how many steps I'm away from x1. Okay, and I'm going to convert it to an integer. Okay, so this is basically the function that I want. So here, for example, let me draw it here. If I'm at x1, x2, x3, and if this is my A, and here I'm at x4, and basically this is going to be 1, 2, 2 and something. So A minus x1 is going to be 2 point something, and if this distance is 1, then x2 minus x1 is going to be equal to 1. So here I get the floor of this is going to give me 2, right? 1, 2. I'm going to be at this value. However, my index, because I don't start counting from 0, but I start counting from 1, I have to add 1 to it. Okay. And this number here, it's a bit of a complicated expression, but this number is going to give me the n for this xn. Okay, so it's going to tell me the index just before A. Okay, so that's it. So I can define x before is going to be x of this n. This is going to be this value here, and x after is going to be x n plus 1. Okay, so here this vn is going to be v, let's call this v before, it's going to be vn, and this v here, let me call this v after, is going to be v n plus 1. Okay, so I have the x just before, the x just after, the v just before, and the v after. So given I know this value and these two values, what's now going to be this thing here? Well, this point here, I can do this by setting this equal to vn, and then I have to add something. Well, what I'm going to add, this is going to be proportional to this distance. Okay, so a minus xn divided by the step, right, this distance here, xn plus 1 minus xn. Okay, so here what we have here, this is this length as a fraction of this length. Okay, and then of course we have to multiply it by how many this decreases, so it's going to be times vn plus 1 minus vn. Okay, so this is basically the formula in order to get to this point. Okay, so then we're going to return v before plus a minus x before, x after minus x before, times v after minus v before. Okay, and this is going to be my interpolating value. Okay, so let's try to implement this in our program. Okay, so here I have my code again, which I added some comments to make it more clear what's going on. So this is the same code as we made in the previous lecture. So the first thing that we need to do is we have to make two grids. Now, one, we have to make a grid which is of lower size, smaller size, and then we have to make a dense grid on which we're going to optimize. Okay, so for example here, let me take the grid to be of size 20, and then we need a denser grid. Maybe let's take the same range, but now let's make it 1000, right? So we're going to have a denser grid to optimize over. And then we need to write a new function, and this is now going to be our interpolation function. So the inputs are an a, right, which is going to be our value of k next, right, the next capital stock in the next period. I'm going to have to input it our grid, this is now not the dense grid, but the normal grid, and then our value function. Okay, so that's good. So first of all, there are a few cut cases, right? So if k next is smaller or equal to k1, well, that's easy. We're just going to return k1. Else, if k next is greater or equal to kn, and here we can use the special command end. So end is going to take the last entry into the k vector. Then we're going to return vend. Okay. And then else we have to do the interpolation thing. Right, so first of all we're going to compute the index just before. Right, so we called this earlier we called this n, so this is going to be a minus k1, right, the distance between the value we're looking after and the start of the vector, divided by the step size of the grid, which is k2 minus k1. Okay, and you would like to have the floor of this, so this is going to tell us the number of steps that we need to take, but this is not going to be an integer, so we convert it to an int value. Now we're going to add 1. Okay, so this is now our value of n, which is going to give you the index just before the value or the entry a. And then x before, so the value just before a is going to be, let me call this k before, it's going to be k of n, and then k after is going to be k of n plus 1, v before is going to be v of n, and v after is going to be v of n plus 1. Okay, so now you have all the ingredients to compute our return value. So return is going to be v before plus a minus x before divided by, it's not x but k, right, k before divided by k after minus k before, and then times v after minus v before. Okay, so let me compile. So I have to compile everything again. We compile the two grids. So here, so I should not put an equal sign here. Right, so interpolation, let us try to do this, right? So let me take a grid x, which is easy as 1, 3, 5, right? And let me take v values to be equal to, let's go 3, 1, 2. Okay. So at x equal to 1, the v is 3, at x equal to 3, v is 1, and at x equal to 5, v is 2. So now let me compute interpolation at 2 of x of v. So now this should be a value between 3 and 1, so it should return 2 if everything is correctly. Okay, a is not defined, so I have made a mistake. So this should be k next, sorry. Right, and probably also here it should be k next. Let's try to compute this once again. Right. Inexact. So I did compute the floor, but I forgot to put brackets for the floor function here. So let's see where this closes. Yeah, so if you have a lot of functions one after the other. It's hard to keep track of all the brackets. So fingers crossed. Yeah, so it gives you the value of 2, right? So, and if I would do this at, let's say, the entry 4, it should give me the value 1.5, which is right. If I would take a number, let's say 7, right, this is outside of the range of x, so it should give me the last entry, which is 2, right? So this seems to work not too bad. So where do we need to enter this interpolation function? Well, basically we first need it where we compute the objective value, right? So now in the objective value we not only need the k, but you also need the k dense grid, right? Because this k next index will be the index for the k dense grid, right? So here we're going to change k to k dense. This computing c is simply the same. C smaller than 0, we're going to return minus infinity. Else we're going to return here the utility, but now here the v is not going to be the v because it's not going to be defined for this k next index, right? Because it's the index at the denser grid. So what are we going to do? We're going to use the interpolation function. Okay, interpolation, and we're going to look for the value of k next, and we're going to use the small grid and then the v function, right? So this should correct for the fact that k next might not be on the grid k. Okay, so you have new objective value. If we compute the max, well, we probably need to also input the k dense grid. This seems okay, this seems okay, but now we want to iterate over the denser grid, so let me call this m. This is now the length of k dense. This goes from m to 1. Here you have to put it, also give the k dense grid. Here also the k dense grid. If value is different from -n. So this seems all okay. So just recall that the opt index now will be the index of the denser grid, right? Because we're converting everything to the denser grid. Okay, so let's compile this, and then this function computes the next iteration of the value function. In principle, I don't need to change anything about this because we're computing everything on the small grid, right? Okay, and also here, normally we don't need to change anything. Okay, but probably we want to, because we need to compute the max, here we need the k dense, so we have to give k dense to every argument. Okay, this is something that I forgot. You have to pass along the denser grid to all the arguments. Also here, probably you have to pass it along. Also here, and so on. Okay, so let's now see if this somehow compiles or somehow runs. Right, so you see, whoa, this really goes fast, right? Have you seen the increase in speed? So the increase in speed here is especially because we only need to maximize it 20 times in every loop, right? Then if you plot, so this is going to take some time to load again. Big library. So now you want to plot k against value function, which is going to be okay because this is of the same size. Now if you want to compute the k at the next iteration, this is going to be a bit more tricky because basically we need to compute it at the k dense here, right? So this will be of the right size, but we need to use the k dense you need to use the dense grid here to compute this. So here we see that we have somehow of a problem here with very low values of v, but otherwise it seems to look alright. So at least I'm going to double check expose if everything in my code was alright. So let me now plot k against k next period. So this looks okay. And then if I also plot the 45-degree line, so here we again have the fixed point, right? But apparently there's some loss in optimality when we go very low. Okay, especially here for the value function, it seemed to be very badly approximated when we're moving for values very close to 0. Okay.